Today we're going to talk about two very important theorems when it comes to basic integrals. The average value theorem and the intermediate value theorem for integrals. These two are very similar and are actually part of each other's explanations. But before we get to that, let's go back to something that should sound familiar. The mean value theorem and the intermediate value theorem for derivatives. The main ideas and concepts for these theorems for both derivatives and integrals are basically the same. So if we can remember the past theorem we learned for derivatives, it will help make this much easier to understand for integrals. So basically, the intermediate value theorem for derivatives states how the instantaneous rate of change, or the value of the derivative at any point along the curve, must at some point equal the average or mean value of the tangent line. In other words, the a-rock, or the average rate of change, must equal the i-rock, the instantaneous rate of change, at one point along the continuous interval. Now let's try an example problem. Let's do this problem here. Find the x value that satisfies the intermediate value theorem for f of x equals x squared minus 4x plus 2 on the interval 2 to 4. So the first step in solving a problem like this is to find the average rate of change. So to do this, we're going to take f of 4 minus f of 2 all over 4 minus 2. So if we plug a 4 into the equation, we're going to get out a 2. And if we plug a 2 into the equation, we're going to get an answer of negative 2. So when we put this in, we're going to get 2 minus negative 2 over 4 minus 2 for an answer of 2. So the next step is to find the instantaneous rate of change. And to do this, we're going to take the derivative of our original function. By using the power rule, we get 2x minus 4. Now that we have both the instantaneous rate of change and the average rate of change, we're going to set them equal to each other. So 2x minus 4 equals the value we already found, 2. Now all you have to do is solve for x. And we'll get an answer of x equals 3. So at the value x equals 3, the average rate of change equals the instantaneous rate of change, satisfying the intermediate value theorem for derivatives. Now let's apply these same concepts to integrals. For derivatives, we were finding the slope of the tangent line. But for integrals, what are we finding? The heights of infinitely small rectangles. So instead of finding the average slope on the interval, we are going to find the average height on the interval. This is called the average value. The equation for finding the average value is written here. It's 1 over b minus a, the integral from a to b of f of x dx. So if we look at this graph here, and we wanted to find the average value, we'd plug in the values of a and b to this equation, and it would give us the average height of the graph. Now let's try an example problem. Let's do this problem here. What is the average height of the graph of f of x equals 2x plus 4 from negative 2 to 3? So a is going to equal negative 2, and b is going to equal 3. So if we plug these into the equation, we get 1 over 3 minus negative 2, the integral from negative 2 to 3 of f of x, which is 2x plus 4. When we integrate this, we get x squared plus 4x from 3 to negative 2. When we plug those numbers in, we get 21 minus negative 4 for a total of 25. Now don't forget to multiply by the fraction out here. So we take that number 25 and divide by 5, and this gives our average value of 5. Now that we understand the average value idea, we can connect this to the intermediate value theorem for integrals. If you recall, for derivatives, it said that the a-rock once must equal the i-rock. For integrals, it's a very similar idea. It states that for f of x, if it is continuous and differentiable on an interval, the actual height of the graph, or the value of f of x, must at one point equal the average value, which is. So if we go back to the problem that we just worked out, we have our average value of 5. According to the intermediate value theorem, there must be at least one point where the value of f of x equals the average value of 5. So to find this, we set them equal to each other. So 5 equals 2x plus 4. Then we solve for x, and we get x equals 1/2. So at x equals 1/2, the height, or the value of f of x, equals the average. Now let's try another example that's a little more challenging. Here's the problem. You are doing a scientific experiment where you measure the temperature of a pond over the course of a month. Once the study is over, you propose that the function p of t, which equals 50 plus 14t e to the negative t over 4, models the temperature for the pond. So for the month, which is from time 0 to time 30, what is the average temperature, and at what time is the actual temperature equal to the average temperature? To start off, let's find the average temperature. This is using the equation that we were given before. So it will be 1 over b minus a, which is 30, the integral from 0 to 30 of p of t, dt. To solve this, you use your calculator and you come up with a value of 57.43 degrees Fahrenheit. Now for the second half of the question, which is at what time is the actual temperature equal to the average? For this, you are going to put both of these into the calculator. So you put in the function p of t, and you graph the answer you just received, which is 57.43 degrees. So when you graph those two things, this is what it looks like. To find the x values that satisfy the IVT for this problem, you just find the intersection points. So as we saw on the calculator, the values that satisfy the intermediate value theorem for integrals for this problem is t equals 12.7 days and 0.620 days.
Now that you understand these concepts, here are some practice problems you can do on your own. Here's the first one. Find the average value on the interval 3 to 6 of the function f of x equals x squared plus 5x minus 2. At what time is this average value equal to the actual value of f of x on this interval? And here are the answers to check once you've completed the problem. For part A, the answer is 41.5, and for part B, the answer is at time. Here's our second practice problem. You are sitting on your deck doing your calc homework when you notice the leaves falling from the trees around you. You decide to create a function that models the amount of leaves falling at any time t, where t is measured in minutes. You find the equation to be L of x equals 7 plus 2t e to the negative t over 5. Find the average value of leaves falling from the trees per minute on the interval 3 to 5. At what time is the average value equal to the actual? Here are the answers for when you finish doing the problem. 10.558 and time 3.819. The first takeaway problem can be done without a graphing calculator, while the second one, a graphing calculator, is allowed. Thanks for watching our video.